All right, next up we have what's called the ideal gas law. So if we take all of the gas laws, Boyle's law, Charles's law, Gay-Lussac's law, and even Avogadro's law, and kind of combine them, we get this. That symbol there means proportional, so volume is proportional to this. And by proportional, we're talking directly proportional. So directly proportional to moles, directly proportional to temperature, but inversely, since P is on the bottom, inversely proportional to pressure. So how do we turn a proportion into an equality? So volume is proportional to NT over P. How do we make that an equality? We're going to use something called a proportionality constant, or just a constant. So I'm going to rearrange it. So we'll put P next to V. So P times V equals N R T. R being our proportionality constants. And so R has a value. And so these values are given to you on your equation sheet, but I want you to see where these values come from. In fact, I think your equation sheet only shows 2 of them. There's 3 different values for R. The different values for R depend on the units for pressure. So remember, pressure can be measured in kilopascals or atmospheres or torr or millimeters of mercury. So let's do this. Let's go ahead and derive the value of R for 1 mole of a gas at STP. So let's take our equation and rearrange it to read R equals. So R equals PV over NT. Okay, so STP, so standard pressure. This time we'll use atmospheres. So standard pressure in atmospheres is 1.00. What is the volume of 1 mole of a gas, an ideal gas, at STP? That would be 22.4 liters. Moles, we said 1 mole. And temperature, standard temperature, we want that in Kelvin, is 273 Kelvin. Go ahead and pause the video and calculate the value of R. Be sure also to include the units. Pause now. 0.0821. I'm going to change the units, the order just a little bit because I'm used to seeing them this way. On top we have liters and atmospheres. On the bottom we have moles and Kelvin. So we read this as 0.0821 liter atmosphere per mole Kelvin. So if the pressure of the gas is given to you in atmospheres, then we will use this value for R. So make a note of that. So example 12.7 on page 413 shows how you can derive another value of R. This time if the units are joules per mole Kelvin, also kilopascal cubic decimeters, which is the same thing as a liter per mole Kelvin. And in fact, let's go ahead and do this. I'm going to go back and I want you to derive the other values for R. So the only thing that's going to change is the pressure. So what if the pressure of the gas is given to you in kilopascals? So go ahead and plug into this equation standard pressure in kilopascals and see what you get for R. Go ahead and pause the video and make sure to include units. Gas is given in kilopascals. The value for R we're going to use is 8.31. Units are liter kilopascal per mole Kelvin. All right, let's try one more. What if the pressure of the gas is given to you in millimeters of mercury or torr? Remember, millimeters of mercury and torr are the same thing, so you're going to get the same value for R. So go ahead and let's change this. Get rid of kilopascals. And go ahead and calculate the value for R in using torr for standard pressure. Go ahead and pause now. Pressure of the gas is given in torr or millimeters of mercury. The value for R that you'll use in the ideal gas law is 62.4 units here, liter torr or liter millimeters of mercury per mole Kelvin. So again, you have two of those, I believe, given to you on the equation sheet, perhaps not this one here. So you can always derive that value. You don't really need to memorize it. You can memorize it if you want. Speaking of which value of R are you going to use in a particular problem? Well, it depends on the units for pressure. And so you can do one of two things. You can either memorize all four, I guess I have here, because the units are a little bit different. So let's fill this out. 8.31 liter kilopascal per mole Kelvin, or 62.4 liter torr per mole Kelvin, or 62.4 liter, sorry, it's kind of hard to read, millimeters of mercury per mole Kelvin. The most commonly used value for R is actually this one. In fact, when I was in college, I used that value exclusively, 0.0821. So you have a couple choices. You can use any one of these four values for R, or three values, I suppose. Or you can just use this one. And if the pressure is not given to you in atmospheres, you can convert it to atmospheres. So choice is yours. Try it out both ways. See if you want to use 0.0821 and make sure your pressure is in atmospheres, or use any one of those. Make sure you use the right value for the right unit of pressure. All right, let's take a look at some examples in the book, starting with 12.8 on page 414. Read along with me, please. What pressure in atmospheres is exerted by 54.0 grams of xenon in a 1 liter flask at 20 degrees Celsius? Walk you through it just a bit. I'm going to use this space for now, but don't write on your notes in that space. We're going to use that for your own practice. So we have this equation. What are we looking for? We're looking for pressure. And so what I'm going to have you do is I'm going to have you rearrange the equation to isolate P. All right, now we can't just plug in all of our values because we are not given the moles of the gas. N is moles, so don't plug in mass there. We are given the mass, so what you can do is, and you can do this all in one shot if you want. The book sets it up in 2 steps. You can take the 54 grams of xenon and convert that to moles of xenon, molar mass being 131, it looks like. And then multiply that by R. So the question asks for the pressure in atmospheres. So we want to use the value of R that has atmospheres in it. That's this one, 0.0821 liter atmosphere per mole Kelvin. Temperature given to us in the problem, 20 degrees Celsius. Notice we have units here of Kelvin. So we need to convert to that Celsius temperature to Kelvin. Take all of that and divide it by the volume. And the volume stated in the problem is 1 liter. So now grams is going to cancel here, moles will cancel here, liters cancels, Kelvin cancels, and we're left with atmospheres. If you want to break it up into 2 steps, that's fine, but I just want to show you can do it all in one shot as well. Take a look at 12.9 just below that. This time we're trying to find the volume. So you would write the equation V equals nRT over P. Plug in your values, everything is given to you. Notice that in the book, what they did is they took the pressure in torr, 748 torr, and converted that to atmospheres. To do that, you need to use the values of standard pressure. So if you have a pressure in torr and you want to convert to atmospheres, use this as your conversion factor. Remember, these are the same thing. 1 atmosphere is the same thing as 760 torr. So basically take your pressure in torr divided by 760, and that'll give you the pressure in atmospheres. If you do that, then you can use 0.0821 for R. If you leave it in torr, R has to be 62.4. Either way, you're going to get the same answer. All right, so go ahead and turn to page 440. And we're going to work on practice problem number 45. It's 2 parts, so please do both A and B. And go ahead and pause the video and do that now. Take a look at our answers here. So first one, we're solving for pressure. We're given the amount of the gas in moles. We're going to use R as 0.0821. Temperature converted to Kelvin, and the volume given to us in the problem, we get 56.8 atmospheres. Letter B, a little different problem. This time it asks for density. Remember that density is a ratio of mass to volume. So we're given the amount of the gas in moles. So we're going to convert that to grams of hydrogen. Don't forget that hydrogen is diatomic. So it has a molar mass of 2.02 grams per mole. Take that divided by the volume of the gas, which was given in letter A, and we get a density of 4.69. Look at the units there, grams per liter. Remember, gases have very low densities. So we're going to express densities of gases in grams per liter versus liquids and solids, which we express in grams per milliliter. All right, next up, go ahead and work on exercise number 47 on that same page. There are two parts, so go ahead and complete both parts. Pause the video now. All right, so as you notice, we have a little different problem. This time we are given the pressure, we're given the volume, and we're given the temperature of the gas. And so what we're not given is the amount of the gas. So we're going to solve for moles. So I broke this up into two steps, beneficial for this problem, but you can do it all in one shot if you like. So I found moles first, 1.63 times 10 to the negative 12. Notice that I used 62.4 for R since the pressure given was in torr. If you converted that to atmospheres, that's fine. You should get the same answer. And then it asks for, in letter A, the number of oxygen molecules. So I converted moles to molecules and got that answer. And then in part B, it asks for the mass of the gas. And look at that. It's a really, really, really small quantity of oxygen gas. It's a really low pressure. So expect there to be not a lot of gas inside the container. Like we're going a little bit backwards here, even though we're moving forward in the book. Take a look at 1211. It says nitric acid, blah, 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 blah. Calculate the density of NO2 gas in grams per liter at 1.24 atmospheres and 50 degrees Celsius. All right, so what do we know about this gas? We know the pressure, we know the temperature, and we know the volume, or do we? So we're going to calculate the density in grams per liter. And so we can plug in for our volume 1 liter. Remember, density is independent of volume. So it doesn't matter how much you have of a substance, the density is constant. If you have a different volume, you're going to have a different mass, but that ratio of mass to volume will be the same. So again, we're going to solve for moles because we need the mass of the gas. And so we're going to use the ideal gas law to find moles, convert that to grams. And then that is the mass per 1 liter. So that is our density in grams per liter. All right, take a look at 41. Go ahead and answer that. Go ahead and pause the video now. So just like the example problem, we're going to use the ideal gas law to find moles. Again, let's set the volume as 1 liter. You can make it whatever you want, technically, I suppose, but we're going to do it per 1 liter. So that way, when we calculate the mass, that'll be the mass per liter, aka the density. So density of nitrogen, 1.38 grams per liter. Notice that the mass, molar mass of air is slightly more than the molar mass of nitrogen, which is going to lead us to get a higher density for air than nitrogen. We get 1.44 grams per liter. Concludes this lesson. We'll have some practice for you to do. Thanks for watching.